Okay, recording is on. Very enough. First, just a quick look to Aula Web. Is it shared regularly or I missed something?
It's shared.
Shared?
Yes.
Okay. Nothing special except the fact that you see here homework. And I want to, today I will try to talk a bit about, in particular, the last topic, signals. I didn't upload so far, just today, because signal is an important concept. We will not do many exercises on that because it's really tricky and complex. Because in principle, it is an important principle and an important feature of all operating systems, but it's surprisingly tricky also in theory. So all system calls are complex. We will do few examples, and I want first to explain and say something. So I decided not to upload in advance, asking you to read. We will do in real time. The homework, you know, it's a suggestion. Oh, probably you don't see this. You see, oh well, it's in our web. You see the document.
Yes, we can see the.
Okay. Because it's inside our web, so it's still shared. So it's the idea of writing a program with these specifications. You have all tools to do that, all the knowledge, because it is based on fork, exact, and on named pipes for communication. Maybe someone of you has already tried to solve or already solved, I don't know. Just a few words, because it's not really, I know, and somebody of you has asked it already, and I promised to explain, is not completely clear probably. The idea is to simulate or just to implement a system that is similar to the publish subscribe method, general method for communication in concurrent systems. I remember, and I remind you that publish subscribe we have seen in the first days. It's a more general and probably the most widely used methods in sparse and big concurrent systems, in which there is a publisher of some data, asynchronous publisher. So it is not given the period of time or the law, the temporal law that the publisher, in this case the G process, observes. So the G process sometimes generates data. In a true publish subscribe, the idea is that the subscribers, so consumers, in a first phase communicate the producer that they want to subscribe all data. So from just after the subscription, all data generated by G, of data of some kind. So data are flagged with the type of data or a definition or semantic definition of data. So G may also, in a general case, may generate several types of data, not in terms of data types exactly from the point of view of the programming language, abstract data type in general of, and each subscriber can subscribe to a particular datum. After a period of time, a subscriber can say, I don't want to be, I unsubscribe, and I am, from now on, I am blind to all data produced of this kind produced by the producer. So, but in general, many subscribers are running simultaneously and receive the same type of data. So this is just a piece of the game, in the sense that we want, I force you to use one only named pipe as a communication channel between the producer, G, and the consumers, S1, S2, and S3. Forcing, well, in this simple case, probably the straightest way is just to provide 3 different pipes, of course, but we want to simulate a dynamic environment in which sometimes a subscriber wants to establish the communication channel. And so we cannot generate in advance, in this case, 3 pipes, 3 communication, so 3 separate communication channels, either unnamed pipes or named pipes, it doesn't matter. So only one communication channel. And this is what happens in a through systems, in which the communication infrastructure is a sort of general channel in which all communication are routed. And I continue to say, you will see in ROS, that is the middleware in which all these communication policies are implemented. So I force you to, the constraint is to use only one, you see, named pipe. Named pipe instead of a pipe, and this is important. And so G generates data and interactively. So G communicates with using the shell. You type a string and say send to 1, or send to 23, or send to 312. Doesn't matter the order, of course. The order is unimportant, but anytime you decide, so you simulate the subscription, an instant subscription that is valid just for this message. So you have to find out how to do that with only one pipe, and this is similar to the solution in a more complex system. So these are the specifications, general specifications. So obviously, the problem is that once G writes in the named pipe the message, the first S1, S2, S3 that reads the message in a named pipe does not erase the message. So the message is still there. So that's the reason why I say the correct way is a named pipe, but you have to erase the for example, you say hello world 2-3. G writes hello world. 2-3 are alerted and asked to read the message, and after they have read the message should disappear, so that for G waits for a new message and so on. So we have to write the algorithm for that. Okay, that's the plain explanation, because someone of you has asked me to explain in details So the algorithm is simple, is a synchronization algorithm, you have to devise how many message G has to send to S1, S2, S3 to ask them to read and to be sure that they have read, and then G erases and waits in a loop for a new message. Okay, that's the most complete explanation I'm able to do. Is it clear for everybody, or other questions? I assume that is clear. Is it still recording? I hope so.
Yes.
Oh, okay, it's recording. You see, I don't see anymore the. Okay.
I see the red dots.
Yeah. I don't see in my screen, probably because of the sharing. Just a remark on this: advanced and challenging. The simplest way of implementing this is just to mimic the two examples, the first .c and second .c, that you can in the example I've presented in the video clip, are two shells separately, and separately you run the two processes. So also in this case, you can open 4 shells and run separately all processes. And that's a good feature. That is a good way of, and as another step towards the idea of testing the execution of single processes separately and not all together, using 4 separate shells. In that case, the name of the named pipe is known by you, so you can so all your processes can use the same named pipe. And since you run all separately, all those processes, you can control completely the processes. You can run, stop, make them run in background. You can kill them. You can do everything you want, even redirect output, for example, for having the output in a file for diagnostics and so on. But another clue possible is, can you make your code so that it opens automatically the 3 additional shell windows? I say difficult because you have to find out the way. And so it's an interesting feature in general in POSIX. So you can decide that one process opens a shell window, for example, for input and output directly from that shell windows. Is it possible or not? Everything you do using the shell, that is a process, you can do also in your process that can run other processes and other shells. So it is possible. And I suggest you, if you want to, it's just an advanced feature, but I think it's also professionally interesting, since if you learn how to write a dialog shell from a process, easily you can have separate processes that can dialog separately, and if they are run by the same shell, of course, they share file descriptors, so it's difficult to talk directly to one of the processes that have been spawned in the tree. Okay, try to do that. I suggest you doing with the first .c and second .c. So find out how to do that, and we will discuss. If the first one we discover next week, can or discovers a method, even if he or she doesn't succeed in using exactly. So we will discuss it in the next Tuesday's class. Now can I go back here? So it's closing the, I have to stop because the button is, I can't see. Now I see that it's recording. Okay, so that's a comment on the homework. Second, I have to go just a minute here. I close this. Second thing I want to discuss with you is the assignment, the assignment that will be evaluated, and I want just to present in more details. We have also to decide the first evaluated assignment is part of the exam, or the final exam. So, and you will have 2 assignments in this semester, and this is the first one, the intermediate assignment. We will have the final assignment at the end of the semester, and then the exam. So we have to decide when will be the deadline for this. I want to decide with you. You know, also if there are other deadlines in the other courses you're attending this semester. So I think that the best way, instead of discussing in real time now, is just to I will put a poll in our web, so you can answer to the poll, and I even and also with comments in some cases. So I will propose 3 dates, and so you will decide which is the best for you, including none of the 3 dates as choice. So please, this week go. But I want first to explain exactly which is the content of the problem, so that you will tune yourself on the difficulty of this. To do that, I have to open the document. The document is this one. Okay. No, I think I opened the wrong document. Yeah, sorry. No, it was the right document. Okay. Can you see the ARP first assignment?
Yes, you can see the slide.
You see the document. So comments. It uses only known system calls. So fork, exec, pipes. In that case, unnamed pipes. And it's a problem that we can consider this problem as a real problem to solve, not strictly related to robotics, but similar to what is needed in robotics when we write a system and want to measure the efficiency of the system or the capability of the hardware structure. And in any case, it's a good example. I've tried with the students 2 years, and so this has been slightly changed considering the difficulties and suggestions by your colleagues 1 and 2 years ago. The idea is that having what we want to measure. This is a receiver data. These are producers. Not even want to write in red. This is a producers. These are producers. And producers are as simple as possible. So just I've written teeny loops. So strict loops, just while one or while true, and do minimum possible lines of codes, just to be very fast, the maximum speed allowed by the hardware or the CPU speed, and by the scheduler, of course. And they produce data. The data is the structure. The structure is this type. Very simple. A key point is the timestamp. A character, just to distinguish the message, but just 1 byte. And is the sequence number. So starting from 0, 1, 2, and so on and so forth. The idea is to run many times, for example, 1 million times. The only problem is that the 32 or probably 64 bits to have the integer. So no, it doesn't matter. But the byte, the payload of the message is not important. Maybe just to distinguish the 2 producers, so they identify themselves with a different character. This is very critical point. Timestamp is exactly the time, the real time in which the message is delivered or, well, is given to the pipe. Timestamp. To identify the real time in which the message has been sent to R, so that we can compute the delay between the producing time and the receiving time. Any message is generated with a strict loop, and the idea is that the loop includes a delay, and the delay is a parameter that you have to assign and to find. Well, of course, in a heuristic way. So you decide which is the parameter, and make some runs with these parameters and so on. We will see after. The parameter as an offset. So this is the real parameter. Oh, parameter. Parameter. The parameter you have to assign and to try in different values. The idea is that you have this as an average value of delay. So the loop of G1 and G2 are delayed in delay, and then, and the delay is not constant as an average value that is a parameter, but can be higher and lower using the random value, and you set with using the system call random. So you have to set up a random generator using the system call to simulate the generation of a quasi-periodic messages. Quasi-periodic means that there is a period. In the average, the period is offset, but can oscillate. So this is generation of messages. Both G1 and G2 generate messages with the same load. There's no need to have different parameters for G1 and G2. We want just to, why having two G1 and G2, to make the system more complex and to use the select. Because the aim of R is to receive as soon as possible data from G1 and G2. So it has two unnamed pipes, and R has to select, even if you know that both G1 and G2 generate data, you must mandatory, this is mandatory prescription, you must select the pipe that has datum, because one of the two is faster, because the delay in the loop changes randomly. So you must apply the select. R receives messages, and receiving as many messages as possible without blocking the generators. And that's the reason why we use the select. At least 1 million cycles. And after you have received all data, you send all data received to M. This is the output of M on the screen or on a file. Number of cycles detected using the number that is in this value. Number of messages received, that must be the sum of the two, or 2 times the cycles. The idea is that the two delays can be different. I didn't put it in this assignment, but in general, the number of cycles and the two offsets could be different. The delay used by G1 and G2, so to have an idea of the experiment, and the delay, the offset delay is, you decide the offset delay. You decide before you run the system, and you compute the latency between generation and reception. How you can compute the latency, what is called latency. So an absolute delay, because you have the timestamp, so the time in which the message was being generated and delivered, and the time in which the same message is received. So you don't have you have to ask the operating system the time and compare with the timestamp. So you will know how much time is needed to deliver the message. And that's the latency. And finally, the bandwidth. Bandwidth means the speed in bit per second. So how many bit per second can be generated and correctly received. That is a value that is unrelated to the latency. You may have a very long latency, even one day, but with a lot of bit per second of bandwidth. So the throughput can be high, but the latency, and as well as the latency, or vice versa, it doesn't matter. So it's similar to what happens in communication in internet. You may have a high bandwidth, and so the speed of the channel is high, but you may have a delay between generation and reception that is called general latency. Probably you know that the idea of the new generation in wireless communication for data, the so-called fifth generation or 5G, is considered to have very good bandwidth, but this important thing they say, it's a very, very, very small latency, so that it could be used for real-time control, for example, because in a loop, you don't have the latency. And latency or delay is the worst thing you can have in a control loop. And probably if the fifth generation wireless communication will be also really interesting in robotics, in particular for distance control. The final aim is to find, by means of experiments, the minimum offset value, such as generator G are not delayed by our code. Because, why delayed? Because if G is very fast, it produces data that are not consumed by R, so G is the speed of G is delayed. So you must find in this experiment the maximum bandwidth so that G runs at freely, and the only delay in, or the only element that constrains G1 or G2 to run at that speed is just the delay that you have decided. But with this delay in the loop, R receives all data. So you must find out, is the measure of the bandwidth or the speed of your computer. The speed in that case includes also the scheduler intervention. We have seen in the past, many students has solved this, and we have a lot of data related to different computers, and the figures are really different. There are hints, and so follow the hints, just hints, practical hints, just to not to decide the parameters in absolutely randomly. Just start with some parameters that are in a range that can probably will drive you to good experiments. And finally, I need this as output. This is the solution of the system. And so we will know how fast you can run a concurrent program with a highly generated rate of data, and how fast, and so which is the bottleneck in communication, in a POSIX communication between elements. So you see that from an engineering point of view, it's a real, absolutely important figure. And generally, you decide to buy a processor or a system, a hardware system, so that because your control system for moving your arm or your mobile robot needs such exchange of data between the modules in the architecture. Remember the scheme of the mobile robot. So this is a problem that is related to many automation, real-time, not strict real-time, or not strict real-time, many automation systems, and robotics in particular. Remember that you need a select, and so the select itself has some parameters. You have to decide, in particular, the timeout. Remember that using the select, you have to wait when R calls select and ask, are there data in those pipes? If there are no data, you wait a timeout time. And if this timeout is too long, of course, it makes the system run slowly. So you have to also decide this. And don't forget, as we have written in the slides, to have a random choice between the two pipes. Every time you have pipes or file descriptors in general, sockets you will see starting from next week. So network communication, and you have to choose one file descriptor with data using the select. Not only you have to wait with the timeout and until you go back and wait again, but also in case more than one has data, you have to choose randomly, not deterministically. So you have to put the random function to decide which one. So that's the description of the thing I want you to solve. There is a, let me say, a good level of professional content. It's not simple. You have to draw a scheme in a sheet of paper with in pseudocode probably, and you have to decide how to write all the elements. M probably is very simple, so it's just receiving data and reporting the output. And try is not difficult to run separately G and R, G1 and G2 are equal, to check if they are correctly written. Don't forget all good policies like error management, in particular error management. So don't forget any component that is necessary. I will also give you just a few guidelines for the good programming style. Okay? Questions about this? No questions. I think it's clear. 2 generations of students had already solved this problem with different success, but in general, they did properly. Maybe some of you find it interesting also because it checks the capabilities of your computer. Someone will find artificial problem, I don't know, it doesn't matter. I think it's really important. So get inside, think of it, think of all the doubts you have or anything, and on Saturday, if you can, if you want, on Saturday meeting, you can ask something. So the idea is that at the beginning of the next week, you can answer the poll to decide when you are able to solve this problem. Not much later, because we have the final assignment that is more complex than this. If there are no questions, I can just, shall we have a 4 minutes break, okay? 4 minutes break. Pause the recording. Good, we can start again. Recording is on? Recording is on, good. Now the next topic is can you read signal?
Yes.
Yes, you read signal. Signal is a POSIX term. In computer science, may have different meanings, but POSIX comes from the Unix experience in the years 70s of last millennium, and the designers of Unix sometimes use some jargon of, well, sometimes, like for example, the system call named kill that doesn't kill. Well, many names are a bit ridiculous today, but this is the POSIX terminology. Signal is the abstraction of the interrupt. In what in hardware is called interrupt, that is the physical value, voltage on some on a pin of an integrated circuit or something like that, that changes the status of the chip of electrical circuit. So an interrupt produces changes in the computational status of the state machine. A software abstraction is signal, so it's an event. So event is another term that can be used. An event is something that occurs at the software level, so without physical semantics, with nothing happens from physical point of view, except the fact that some algorithm receives the raising of that event. Something changes. So no datum is implied, except the fact that that event occurs at that time. So event is a couple of values. Theoretically, is the time in which it occurs, and the name of the event. We suppose that we have several possible events distinguished by name with different semantics, so they will produce different consequences on the software on the algorithms running. And the important thing is that they happen at some time that is real time. Not computing time, not a time related to the progression of the computation of such of an algorithm. So it happens exactly in the time, whatever is happening in the computation. So the idea and the POSIX model for signals is that an algorithm, so a process, let's say a process, is executing lines of code. A process before executing this code. So this is the body of the process and can do anything. No constraints. Process is executing, but before executing the code lines, or if you want to be more precise, in the beginning, just in the beginning, it decides a handler. This is the function. Is a function. It's called handler of a specific event, of a specific signal. The handler in its turn is a function with several lines of code. But it's a function. So it's a function exactly. So it has a starting point and returning point, and it is executed in the stack. Suppose that some other process or the kernel itself raise an event. Suppose that the process is executing this line of code. The semantics is very similar to any interrupt at low level, hardware interrupt. So the execution of the process is suspended and the return point is stored on the stack. So the process can be resumed. If you remember, in the process table, there is written the process computational status so that the process can be resumed, is interrupted just exactly like the switcher does when it decides to interrupt the process. And exactly what happens when a hardware interrupt comes, so the kernel stops the process because it is executing the interroutine connected to the kernel. So the process is suspended and the thread of execution is transferred to the handler. So the function connected to the handler, well, defined as handler, you will see that the handler is you decide the function pointer. In any case, it doesn't matter, the name of the function executed, and upon return of the handler, the process continues execution. So it's a limited interruption that may occur anytime. So it's a real time of execution, not an abstract time or status of the execution. At the time, maybe this line, anywhere. The process is interrupted, you execute the handler, and upon termination of the handler, the process continues. Or in some cases, well, different cases may occur. Let me say that also the kernel, so another process the two processes, those two processes, the receiving processes and the raising, emitting processes, declaring the event, must be of the same owner. So in your process tree, in your process family, any process can send a signal, an event, to any other process. You cannot send events or signals outside the process tree of an owner, and this is very important for, of course, for safety reasons. The kernel can raise any kind of events of signals, of course, to any process. The kernel can do. Some events are generated by the kernel after some hardware interrupts occur. Generally, this is due to some errors. For example, the classical dividing by zero floating point error or illegal instruction or something like that. So there are signals that can be delivered in this way. So this is the whole logic of that. I've missed one important information: the name of the signal. The name of the signal must match with the name of the handler, in the sense that signals are different. You have many signals, tens of different signals. So the possibility of executing tens of different handlers. So you must match a signal to a specific handler, and the matching is on the name of the signal. You will see how to specify them. It's not the name of the handler, not the name of the function, but the function is declared as matched to certain name. How many signals? Now we will see the slides. This is a sort of general introduction using my childish drawings, so that probably the slides can be understood more clearly. Tens of signals. And the important thing is, another important thing is, if you don't specify a handler for a signal, what does it happen? The signal is received, ignored, or not. For safety reason, well, the decision in POSIX is that in general, not, you see the exception, in general, a signal without handler makes a sort of, activates a sort of default handler. Default. Okay. Good. Default handler. Should be terrible if you had to write handlers for tens of signals always. You don't write any handler, so default handlers are activated. The surprising fact is that in general, in general, the default handler is exiting the process. The decision is so dramatic because maybe you have forgot to decide what to do. So you forgot to write a default handler, or you could not foresee that some signal may be activated. So to be sure, if you receive a signal and you do not handle the signal, in most cases, you will see the difference in which are the cases the process exits with error. This is another important situation. Not going into more details, some signals have only the default handler, so you cannot write the default handler. So they're the so-called strong signals. To be sure that they are so important that you cannot decide to treat them differently. And this is another security issue. Another security issue is that few but very limited number of signals do nothing. So you can also forget to write the handler. And there is also the concept of mask. It's a tricky concept, but it is important. If you put, as we will see, all signals on a table, with they are distinguished by an integer number, just like process IDs, like just group IDs, like just users, and so everything in POSIX is an integer number. So if you have you can have a bitwise mask. So if you put the number, an array, a bit array, the position refers to a signal. 9, for example. 9 is a terrible signal in the 9th position. And you put here 0 or 1. And you can decide to mask signals somehow in several situations. You have the possibility of specifying in your process which is the mask. Mask means that the 0 value in the position of that signal masks the signal so that you will not receive that signal in any case. So you don't need to specify a device handler. The device has a signal handler. If you put 1, you listen the signal. Good. We have already seen the signal mask in the select, because before going inside the details in the slides, we could think that signals are very powerful way of making process in a concurrent system communicate each other. So if you have data, you can just signal to the receiving processor, I have a datum, so just please read. I don't have problem of selecting the pipe for communication. I just communicate that I have something to do. But signals are really tricky because they do not work in the conceptual space of algorithms, but in real time. So the real space in which algorithms are computing. So it's very difficult to foresee when a signal will be received. Maybe in some critical situation while you are writing on a hard disk, so you must not be interrupted. So in that case, you have to mask the signal. but the signal may contain some important information. For example, I have a new datum for you. So there are many situations in which signals cannot be widely used as a communication method, general communication method. Otherwise, no pipes, no file descriptors, no thought would be necessary. You just say, you just communicate using an event to some process that something has to do. You put all the receiving part in the signal handler and you carry on your work. But what happens if the signal arrives while your process is in waiting state, is not running? Is there a queue of signals or not? Just like interrupts. Are signals enqueued, and when the process from waiting states becomes running again, already the signal queue is processed in the order they have been received? But if the signal is not the first in the queue, but is later on, but is more important than the first one, so it should erase a signal in the queue because it's not necessary to receive the previous one. So signals are, from a logical point of view, cannot be used in general for synchronizing processes. So they widely used to notify a really important situation that require a change of the state of the computation of the process. And in most cases, they're used to raise alarms or to change completely the evolution of the system, or to signal, and that's probably the reason of the name, to signal anomalous situation to be managed. So we cannot rely on signal handlers like doing nothing but recovering activities. That's the general idea. So we have time just to grab the slides. Is it clear so far? Shall we go on with the slides? I have slides somewhere. Okay, POSIX Essentials. Okay. Signals. I already told that. Well, let me stop share and change the dimension of the screen. Okay. Okay. Can you see the signal schema?
Yes, yes, we can
Yes,
see
you
it.
can see. So this is an example using real code. Suppose we have the process 23555. Numbers are absolutely randomly chosen. So, and we have another process. The process 23000 must be of the same part of the same family, means that they owned by all the two processes are owned by me. The first process, main, is just executing some lines of code. And during the execution of the process 23000, the process is calls the system called kill. It's funny, but kill is just raise a signal. And the parameters are very simple. Destination. So the target process is this one. You know, you see here, I can't see the, okay. This is the destination. And this is the name of the signal, the number of the signal. Signals we will see in a table are numbers, and there is a defined file, so a general file in which you can use the symbolic name instead of the label instead of the number, but they are integer numbers. So it sends the SIGINT, the interrupt, and fortunately, main has written, compiled this SIG handler, the function that I called SIG handler, maybe any name, of course, with the parameter. The parameter of the SIG handler is exactly the number of the signal. The SIG handler receives this and prints a message. After execution, just on exiting, it returns here. So you see that it's very difficult to write a coherent concurrent process, since you have to take into account when and in real time this process will send this. The effect is similar in that case because here there are no changes in computer status, but suppose here you assign some variables, that is a global variables, x assign 7, okay? And suppose that here there is the int x equals 0. The variable is shared because at a file level by the handler and by the process. So sometimes in that case, the value of the variable x that before receiving a signal was 0, after receiving a signal is 7. But this not happens exactly in this line, maybe here, 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 everywhere. So you see that communication using signals is very difficult, since you notify some changes in the computing status, but depending on the real time. That's the structure. Let's browse the, okay, most common signals. You see here that the number of signals that are not in order. The SIGINT we have using this example is this one. Number 2, you see that all default actions correspond to actions when you do not write the signal handler. And you see that in most cases, what happens is terminate the process termination, except for those that are special interrupts that you cannot catch. Catching a signal is another jargon used to say that you have a signal handler for that. You catch a signal. You cannot catch them. You cannot use it's no meaning if you write a signal handler for that, because they have default action used by the operating system itself and by the shell. We will show after. Just an explanation. Core dump. The core dump is an important debugging activity in POSIX. That means that the process is terminated, but the core, the memory, the memory, the whole memory of the process is saved into a file that is named core. You will find in the working directory a large file called core, and is just an image of the process that is being terminated. Why this? Because in particular, those signals usually are raised when an error occurred. So probably for debugging purposes, you have to analyze the core. And there are analyzers of the core, both use with the shell or with the graphic interface that you can go inside. It's exactly the core they examine when you use a graphic user interface for writing programs, and you put a breakpoint or something like that. You analyze what happened. So you can say, you can spy inside the program and know exactly when the program was terminated, which were the values of all variables and everything. So we don't spend time on that, but it's important to know that if you develop programs at this level, you have all the tools to analyze also terminated, killed, or died processes for unknown reasons. And you see that in any case, if you don't manage the signal, the process terminates. How to write? The example. Where is it? Just how to write the signal handler. There are two ways to call. The SIG action is POSIX. So this is the real POSIX portable primitive. It's more complex than signal. Usually in many situations on fast prototyping, on the exercise and so on, we use signal because it's simpler, really simpler and elementary, but it's not POSIX. It is a C library. To raise a signal, use this, we have already seen. PIDT is the predefined type that is an integer. This is an integer, yes, the predefined type, not for the signal, but for the process ID. We already encountered in weight and in fork and so on. C handler is a complex type that is used to define the signal. We'll see it has many information inside. This is the important information, the signal, the name of the signal. Another important information is the pointer function after having received this signal. This is the signal handler. The SIG handler, this structure is used in the here. This is the simplest handler. You see, very simple. But if you use the SIG action is a bit more complex. This is the signal. You must specify the structure of type SIG action. A pointer to this. This is not important, much important. You will see here how is the SIG action made. You may specify the handler and other information. This is the pointer to the handler, so the name of the function. This is an alternative function. We don't spend time on this. This is the mask and many flags. In general, these are the only parameters needed. Any other parameters can be set to 0. Sorry, I ran a bit out of time, so I stop here. We will finish the presentation of all details. Please read them before next week, and upload also the examples, so you can run the examples. There are absolutely the same examples you can see here in codes in the slide, but just extracted from those slides. You can run them directly and see what happens. And you will see also a very simple example of assignment on signals that you can do by yourself. So sorry, it's time to leave. I think you have no classes after, but there's no reason to go later than this. If there are questions, please raise now or on Saturday or in any time, as told to most of you, and I repeat myself. If you want to talk with me directly, please send me a Skype message. My address is, Renato.Zaccaria on Skype. And send me a message, and we will decide together to have a direct meeting using Skype. Okay? So for me, it's enough today, and thank you for joining also the class this day, and the first day of curfew in Genova. I hope that situation will improve in the next days. Okay, I stop recording.